Hi, I'm Anna Tapper, and in this bite-sized session, we're looking at developing mathematical understanding through language. This is part of the Spring Term CPD for 2023. Many of you will be familiar with a poster of keywords designed to support pupil understanding of word problems. A simple key. If you see this word, you know what operation to complete. Many of you will also be familiar with the acronym RUCKSACK as a problem-solving tool, which asks pupils to underline keywords to help them identify an operation. However, mathematics and language is not that simple. By teaching keywords as a method to identify an operation, we are not teaching children how to think and reason mathematically. Let's look at these problems. Pause the video here and consider the use of the terms total and altogether. In the word list, total is identified as a synonym for addition, and altogether as a synonym for addition and equal to. However, these questions are complex and require deeper thinking. So if using language as an indicator of a process is not straightforward as intended, what should we do? Nick Hart suggests an alternative. Instead of teaching that problem solving is a skill, we should teach children the inherent ambiguity of vocabulary in different contexts, the underlying mathematical structures and common problem scenarios. When it comes to vocabulary, we must show children how a word or a phrase can mean different unknowns. When teaching additive reasoning, any problem is either one where the whole is unknown or where one of the parts is unknown. For multiplicative reasoning, there are 3 underlying patterns, which yields 5 basic structures in total. So let's have a look at how these structures could help us to solve the problem. In this question here, the only mathematical word that might support us towards finding a procedure is total. But we need to know more than this. So I'd start by pulling out what's known and unknown and developing a rich mathematical discussion with my class. I can see here that the whole is unknown. I know what each part is and how many of them there are, I just don't know what that totals. So I know there are 23 parts and each is half a kilogram. So I know that 23 lots of a half means I'm going to do 23 multiplied by 1/2. Or perhaps I might like to think of it as 1/2 of 23. In this question, again, the only mathematical language to support me is altogether. The context is something that will be familiar with most children. They understand what running laps means. So here I think again, what's known and what is unknown. Can I draw something to support me to understand what the question is asking me to do? Here I know the parts, that there are 252 children who take part, and that each child runs 17 laps, but I don't know the total. I know there are equal parts of 17, and that 252 children run each one of those laps. So I've got 252 17 times. I've started to draw a bar model. However, I've recognised that actually this has now supported me to understand the structure. I know what arithmetic procedure I need to do, and it's long multiplication. Let's look at this question together. Pause the video here, read through the question carefully, and think about what is known and unknown. When I look at this question, one of the things I know is what it's asking me to find. It's asking me to find the total number of cars parked in the car park at 10 a.m. An unknown is how many cars are parked. There's no information about that. I know how many spaces there are available on each level of the car park. And I also know how many empty spaces there are on level 2 and how many empty spaces there are on level 1. Now I can start to use this information to think about how I'm going to solve the question. My first step is to use what I know about the spaces available to find the total number of spaces available in the car park. So I know that each level has 800 spaces. I know the two parts, but my whole is unknown. I'm going to start by adding together my two parts to find my whole. Now I'm thinking about the empty spaces, because the empty spaces are going to give me an indication of how many cars are parked as well. I know that on level 2, there are 511 empty spaces, and on level 1, 268. Again, this is additive reasoning. I know my two parts, but I don't know my whole. Once I've added those together, I now think about the parked cars. Again, we're looking at additive reasoning. I know the empty spaces. That's one part. I know the whole. There are 1,600 spaces available, but the bit I don't know is the parked cars. So now I can subtract my empty spaces from the total spaces available to find the parked cars. Let's have a look at this problem and think about how our structure of what's known and unknown can help us when a problem doesn't have any keywords at all. Pause the video here and think about how you might discuss this with your class. Some children may be initially drawn to a mental model of an array when thinking about the 15 melons in a tray and 3 trays in a box. They may wish to draw it out like this. Other children may wish to draw it as a bar model. Either way, what we're saying for this one is that we know the parts, that there are 3 equal parts of 15, but we don't know the whole. So we know that's multiplicative reasoning. Then, once we know the whole, we have the second step in our problem. There are 45 melons in one box, but the supermarket sells 40 boxes of melons. So what do we know here and what is unknown? We know that in each box there are 45 melons and that the supermarket sells 40 of them. So 45 multiplied by 40. Again, we know the parts, but the whole is unknown. This leads us to long multiplication. Discussing the question and the context is key here. Increasingly, we're finding that questions are designed like the two we've just looked at to ensure that pupils cannot just complete an arithmetic procedure using keywords. It's therefore important for pupils and teachers to have a common vocabulary and understanding when discussing maths. Ideally, this would be shared across the whole school, thereby avoiding concepts or vocabulary appearing to change. The word sum is a classic example of this. Previously in primary teaching, we may have used it inaccurately to mean any calculation. However, now we use it correctly to mean the answer to an addition calculation. Pupils are becoming increasingly proficient in understanding specific mathematical terminology, such as vinculum, subitise, and equivalence. However, the area they are less confident in is using this vocabulary to explain their mathematical thinking. STEM sentences are used to ensure the use of mathematically accurate language, to avoid misconceptions, and to explain your own expert mathematical thinking. They're used to support children to recognise what is known and what is unknown, and build connections between different mathematical concepts because they give structure to mathematical thinking. Essentially, a highly structured STEM sentence provides pupils with a way to communicate their ideas with mathematical precision and clarity. They can be used to express a key concept, generalize a key concept, or to provide a template for discussion or explanations. Putting STEM sentences with the key vocabulary on your slides will act as a prompt for you and a scaffold for your pupils. For mathematics mastery, these slides are provided for you, such as the examples here. They not only have STEM sentences, but also examples of pupils' mathematical thinking, along with the key vocabulary. Take the time within your lessons to really explore what these pupils are saying and to use it as a scaffold to build upon your own pupils' mathematical thinking. They should be using the STEM sentences accurately to ensure there is structure given to their own thinking. In White Rose, the STEM sentences are not provided as slides, so this is something you need to add in yourself during planning. In the notes and guidance section, for each small step, there are some suggested possible STEM sentences. You can take these and put them into your slides, along with the key vocabulary, and think about how you would use them to support pupils' mathematical thinking. Using a my turn, our turn, your turn approach gives children an opportunity to hear mathematical language and explanations before trying it for themselves. As STEM sentences and the use of full sentence answers become part of the expectations in class, pupils will become more proficient in explaining their thinking. These are the next steps I'd recommend. Discuss the use and teaching of mathematical vocabulary across the school. How do all adults model this? Are children using mathematical vocabulary effectively to aid their thinking and bring clarity to their explanations? I would change from looking at keywords or rucksack as a problem-solving approach to asking what is known and what is unknown. Introduce children to the problem-solving approach that supports this and model the use of representations to support understanding of the structure. Particularly if you're a White Rose school, develop the use of STEM sentences in your own class and across the school. Insist on full sentence answers and explanations to questions, and model to explain your own mathematical thinking, accurately using mathematical vocabulary. And don't shy away from discussing vocabulary that's not mathematical, but can be problematic. Thank you.